Okay, so what I'm going to tell you is about some efforts in my group about the certification of many-body quantum states. So my group is mostly about quantum information theory, but of course we are interested in problems in many-body physics or quantum optics as well. So the certification problem, I think, is very general, and it has been mentioned in several talks during this conference. So at the moment, we are preparing, I'm not, so people are preparing complex quantum systems, and there is a need of developing efficient methods to say relevant things about these systems that are being prepared. So I will start by maybe a very typical problem in quantum information theory or in quantum physics in general. So we have a system, and we have to say something about this system. So for instance, I'm going to focus more on the question whether this system is entangled. So someone prepares a system. Here's the system for you. I'm a theorist. I have to design tools to say whether the system has some relevant quantum properties. And this is challenging when the system is big because, well, first we know that if I want to fully reconstruct the quantum state of my system, I need to estimate an exponentially growing number of parameters. So it requires a lot of effort. And even if, let's say, by some methods you are able to get the state of the system, sometimes detecting a given quantum property is also challenging. So you need to solve a complex optimization problem that requires, this is just a theoretical problem. So even if you give me the description of the state, to detect some quantum properties, sometimes I have to solve a complex optimization problem that, again, involves an exponential number of parameters. So in a way, you need to solve these issues. So you need to have efficient ways of extract relevant information from the data you get in experiment that often is a set of restricted data, not enough for a full reconstruction. So this is the first thing I'm going to consider, and I also want to, usually in my group, we work a lot on something called the device-independent approach to quantum physics, and I'm going to illustrate this because I think it's also relevant for quantum estimation problems. So what is, from a theoretical point of view, from a formal point of view, what is an estimation problem? You have a system that is being prepared. Maybe this system is subjected to an evolution, and then this system is measured. You apply different measurements to this system, and you have R possible results, and possibly you have P possible preparations. So these preparations are just, you tune some knobs in your lab, and then here you put some detectors in some given positions, and you detect which, you see which detectors click, and this gives you the results. So at the end of the day, what you measure in the lab is this, the probability of observing some results when you prepare some states and you measure some systems. So these are just labels that you have that determine the actions in your lab, your microscopic actions. And then we theorists attribute physical modeling to these labels. So we say that when you put given stuff in your lab, it means that you prepare the state rho 1. But okay, this information is not available in the lab. This is your modeling of the setup. So what you want to do then is you want to infer about properties about these objects from what you see in the lab. This is an estimation problem. So if you want to know the state, usually we assume that there is no evolution. We assume that we know these measurements, and then since we have this in the lab and we know the measurements, we invert the problem and we estimate the state. So if we have this is what we get in the lab, and we assume that we know this, I'm assuming there is no channel here, okay? Then I invert this system, and I can reconstruct the state. Well, this is valid, okay? This is what is usually done. But I want to stress something. So when you estimate the state or the channel or the measurement, when you estimate any of the elements here, you assume that you perfectly know the other elements. This is why you can invert this equation, okay? So if I want to know the channel, I assume that I know the states, I know the measurements, I have this in the lab, I invert the problem. And you assume that this is perfectly known, so you know what is all about what is missing, you have perfect knowledge of that. I think in some situations this might be arguable. I think it's a strong assumption. And I always illustrate this. From this picture you can see that I'm a theorist. Probably this is a setup from the years, I don't know when. But I think it's debatable to assign a Hilbert space dimension to that, okay? And this is what you do in any estimation problem. So this is why we advocate that in some situations it's nicer, cleaner, if you can say things about your system only from the statistics without making an assumption about the objects here. Okay, and this is what we call the device-independent approach to estimation, because you say things about your devices only from the statistics without making any modeling, without assuming any Hilbert space dimension for this setup. OK, so this is the first problem, state estimation. The second problem I want to consider is certification of computing devices. So a second very active research direction is the following. So you have also, again, a complex system in the setup, and you use this system to compute the properties of a classical or a quantum system. So if it's a classical system, I will talk about quantum annealer and a quantum system and simulator. And basically, these systems give you the ground state and the energy of a given system of interest. And you use this system to get a solution to this problem. Well, strictly speaking, what the quantum system gives you is a possible realization. You don't know whether this is the optimal. You believe that it will be the optimal because you have some theoretical assessment of your setup. But strictly speaking, it's just an upper bound to the ground state energy, and the state is the state that gives you this upper bound. So what we want to know, is whether this output is good, okay? Whether it's close to the actual unknown ground state, the solution to your problem. And I think this is also an interesting problem, because if you look at many of the methods that exist, DMRG, Monte Carlo, you name it, many of these methods, they are variational, so they explore things within quantum physics, so they give you other upper bounds. So, well, this is good for certification, because if the classical methods give you lower upper bounds to the ground state energy, you know that your quantum system is not good enough. But I would say that even if the quantum system beats all your known methods, is this good enough? Well, I don't know. Hopefully, yes. And I think this is also a problem, because we expect that for difficult problems, you will have a very rich landscape of local minima. And it could be that your quantum solution gets stuck in a local minima, while the real solution is close but in energy, but it has very different physical properties. So I think it would be nicer to certify this problem in a different system. So these are the two things I want to consider. Okay? There is a problem of state estimation, and there is the problem of certification of outputs of quantum computing devices. Okay, so the problem is challenging because difficult, because these systems are hard to characterize, and you have many parameters. So we are facing a complex optimization problem. So what can you do in this case? Well, a possible solution is just you breathe and you relax. Okay, and this is what we are going to do. So we are going to relax. And a way to relax that I'm going to propose is the following. So when you read at this, it doesn't seem a very relaxing way, but I will tell you why this, I think, is a valid approach for that. Okay? So I'm going to use something that looks very mathematical. I'm going to tell you how it works in a very simple terms. So I'm going to use this hierarchy of semi-definite programs to solve polynomial optimization problems. Okay. So my goal is to make you understand why we believe that this is a promising approach, and why this is something that you can use to relax these problems. So what is polynomial optimization? This is just a mathematical parenthesis, but with very little technical details, very few technical details. So what is a polynomial optimization problem? Well, it's something that we have all encountered in our careers. So you have a polynomial depending on some variables, and you want to minimize this polynomial. Okay? This is the solution. And these variables are subjected to some other constraints that also have the form of polynomials. You see here, this Q and P are polynomials of a given degrees on these variables. Well, just to put sometimes it's good to have an example. So this is an example. Okay, you want to minimize this polynomial of variables x1 and 2, x2, and they are subjected to these inequality constraints. When an equality constraint, you can always write it as two inequalities constraints. So equalities and inequalities constraint. Okay, this is an example of this generic polynomial problem. So let's just put it in figures. Sometimes it helps. So what I have here is have a region. These conditions give me a region in Rn that I represent by simplicity with this region here. Okay, this gamma bar. Okay, this is the subset. Okay, it might be more complex than that. It might be non-convex, but for simplicity, I represent it as this set here. And then you have a polynomial, and you have to find the minimum of this polynomial in this region. This is the problem I want to solve. And of course, this problem is difficult because you may have many minima, local minima, okay? So the solution I want to find is that one, which is a minimum within this region. There is another minimum, but it's outside my region. Okay, I'm not interested in that. So this problem, it appears in many instances. There is a nice way of addressing this problem, which was proposed by Lasserre and Parrillo, okay, in the, well, maybe 20 years ago, I don't remember now. Okay, so basically what Lasserre and Parrillo proposed was, okay, forget about this and replace this set of interests by other sets. And the nice advantage is that these sets are much easier to characterize. And what do I mean by easier? Okay, if you don't know this meaning, you can characterize these sets that replace the original set by something called semi-definite programming. This is something very efficient on a classical computer. You can download a package, and you can run semi-definite programming on your laptops. Okay, I'm not going to explain what semi-definite programming is, but it's just something that you can efficiently solve on your computer. So what's the intuition? So the intuition is, this is the set you want to, over which you want to minimize, and these people gave you other sets that are larger than the set, but that are much easier to characterize. And the nice thing is that they give you a hierarchy of these sets. I mean, the characterization of this set becomes more and more complex, but there is a very good property, which is these sets tend to the set you want to characterize. So what they tell you is, like, rather than solving this difficult problem, solve this problem, which is much easier, and then you will find eventually the solution to the problem. So for instance, in this instance, if you run the first step in the hierarchy, you're looking at the minimum of this polynomial over the set gamma 1. Where is the minimum? The minimum is there. It's not what you want. So it gives you a lower bound to the solution. When you run over the second set, you will get the same solution. But if you run over set 3, you will already get the third solution. Okay, so this is, I hope it is important. It is important that you understand what I'm saying, at least geometrically. Okay, so you have sets that get better and better approximations to the set, and these give you lower bounds to the search solution, because the sets are included in the final set you want to characterize. So you get lower bounds to that. And some years later, we generalized this method to the quantum case. So that was for commuting numbers, variables. So we generalized this method to the case of non-commuting variables, operators. So you want to, this is a polynomial sum operators, you want to minimize the minimum eigenvalue over states, and you have some other polynomial operators. But the logic is the same. So you have a set, you want to find the minimum, and we, again, gave a hierarchy that approximates to that. It gives you lower bounds, and it converges. The logic is the same. Okay? You have a set that is hard to characterize. You approximate this set by outer approximations to this set that are easier to characterize, and by definition, you get lower bounds to your search unknown solution. So how much time do I have, Chairman? 12. Okay, so now let me go to the first problem. So I want to know whether the system is entangled. Okay, this is what we did in this paper with Flavio, Danny, and Peter. So basically, again, what's the logic? You go to an experiment, you collect statistics about your setup, and you want to know whether this statistic is compatible with an entangled, with a separable state or not. If it's not the case, then the state is entangled. What you can see is that so I want to know whether some statistics are compatible with a separable state, measurements acting on a separable state. Well, believe me, this is equivalent to saying whether these statistics is compatible with commuting measurements on a state, where all measurements commute, not only these measurements, but even the measurements performed by one party. So something is compatible with an entangled state, or with a separable state on don't violate any Bell inequality, and equivalently don't violate any Bell inequality, if they can be written as commuting measurements, but everywhere, also these measurements commute, okay, on a quantum state. So again, the experimentalist gives us this, and we have to tell him whether the data she collected in the lab are compatible with a separable state. Because if not, what is in the lab is entangled. Okay, this looks something complicated, but you can write it. What I'm demanding is whether the numbers observed in the lab can be written as a combination of these operators, but this is nothing but a polynomial over these operators. So this is what the experimentalist observes. So just measure data. I can run whether these numbers can be written as polynomial over operators. So I can use the mathematical structure I was telling you to solve this problem because I'm dealing with a polynomial optimization problem. It's not a minimum, but you can turn it into a minimum, so this is not a problem. So what I want to know is whether my numbers, my statistics, has a local model or is separable. What I'm giving is outer approximations to this set. Okay? First step in the hierarchy, second step in the hierarchy. If a point is not in L1, for sure it's not in L, so the state is entangled. So we applied this method to some configurations. So for instance, let's imagine that you have a W state, and you measure sigma x and sigma z, and you take all 4 body correlation functions when you measure x and z. So the number of data I'm going to ask from the experimentalist grows polynomially with the size of the system. I'm going to ask only that the experimentalist measures these 4 body correlation functions. We run our method, and we can see the entanglement in the state up to 29 particles with this information. But the nice thing is that all the effort grows polynomially. I can run this up to 29. This is impossible by any brute force method. And the number of measurements scales polynomially. And we also did this for the GXZ state. Again, we can tell the experimentalist to measure these observables, and we can check the entanglement up to 30 particles. Actually, in this case, we could make everything analytical, and we now have a method that scales with F4 n to the power of 4 that detects GXZ state up to a noise resistance of 14.5%. Okay, so in this particular case, again, the logic is you give me some data, I run this method, and I can sometimes, if I'm lucky, in these cases I was lucky, I can tell you if the state is entangled. Now, second problem, certification. So now I remind you that the problem is that I have a system that gives me a possible ground state and energy for another system, and I want to know whether this is good. Okay, this title is not, this is something that we are working on with Christian, who might be here, Flavio, and Peter. So for the moment, we are working for the classical problem. So I have a classical spin system, and I want to find, with some random couplings, disorder, and I want to find a solution. So people are proposing the use of quantum annealers to solve this problem. So again, the quantum annealer gives you, this is the output of the annealer. It gives you a state, an energy, and a configuration. And we know that this is a ground state, an upper bound to the ground state, energy, and which we don't know. Okay, so we know, all what we can say is that the output of the machine is an upper bound to the unknown solution. What is that? Well, this is just a polynomial over these variables, sigma I and sigma j, the spins. And we know they are spins, so they satisfy these equality constraints. Again, another polynomial. So I take all previous machinery, and I can apply here. So what is the nice thing? The nice thing is that I was telling you that these things approximate quantum physics from the outside, or the set from the outside. So you will get lower bounds to the unknown ground state energy. So now, using this method, I can tell you how I can tell you what the gap is between the ground state and your output of your annealer or the output of our method. So I can approximate the ground state now from the two sides. Okay, we are not the first ones using this method. These methods have been used, but we apply also some other tricks that were very good in this particular case of classical systems. So for instance, it's very easy from, I'm not going to tell you how because there is no time, but from the method, it's also very easy to get an upper bound. Not necessarily the one given by the quantum annealer, but you can also get an upper bound for the classical spin systems. And this is good because then you can combine and have upper bounds and lower bounds from the same method, and you can play with it, and you can close the gap and even find the exact solution to the classical spin system. I'm not telling you how, okay? So what I told you is that our method gives you lower bounds, but for classical spin systems, we also found a way of getting an upper bound, and now we can play with that and close the gap in general and find the exact ground state energy of the classical spin system. Okay, I don't think we are the best in terms of scaling, but we can solve systems of large size, say 1,000 particles, in 2 hours. Okay. So what we did then, we took this algorithm and we were running in a D-wave machine. Okay, we could have tested many systems. We took a triangular lattice. So we were running some spin models on D-Wave, and we're running our method. And in most of the cases, our method and D-Wave were given the same value, but in some cases, they were not coinciding. So our method was better than D-Wave. Actually, in some cases, D-Wave was not given the right value, so we were trying again, and then D-Wave was given the value. But in some other cases, D-Wave was, at least at some point we got tired. So D-Wave was unable to give the same value as us. Okay, remember, in this case, we are getting the exact value of the ground state energy. So for instance, here, D-Wave didn't give the same value as us, but we tried, and in the end, we got it. Okay, it was more or less the same. I don't know if you can read this, but this is, for this instance, it's the same value. As you can see, the configuration is the same. But it's nice because there are some situations where the energy is reasonably close, but the configurations are very different. Okay? And here, it means just that the quantum annealer goes stuck in a local minimum. So what is next, and this is what we would like to do in the future, is to move this system to quantum systems. So we want to study fermionic operator problems and then to certify the output of quantum simulators. In principle, the techniques are there, okay? So because what is a fermionic system, Hamiltonian, is just a combination of, well, I wrote this, but it can be whatever, okay? So just a combination of creation and annihilation operators. And again, the output of your simulator gives you a possible upper bound to the ground state energy to the unknown ground state energy. So this is nothing. Again, I take this. This is just a polynomial of these operators. What are these operators? These are creation and annihilation operators, so they satisfy some polynomial constraints. So again, this is a problem that I can put into that. And with my method, I will get a lower bound to the unknown ground state energy that I can use to certify the output of simulators. Well, here things are more complicated, but in principle, the tools are there, and we are working on that. Again, these things have been considered in the past. So it was for us a surprise because we had these ideas we wanted to use in a many-body context, but if you look some quantum chemistry problems, these methods had been used by people like Nakata and Mazziotti in the past, similar methods. And also, there are some papers studying these methods in the 1D case with short-range interactions, but we want to go into the 2D case, which is more interesting. So I think I'm just presenting this as a way to certify quantum simulators, but of course, it's also another way of certifying classical simulations of quantum systems. So you have a Monte Carlo, DMRG, and tensor network algorithm. They all give you upper bounds to the ground state energy. So this method you can also use to certify the output of a classical simulation technique of a quantum system. Okay, so with this I come to the end. Well, I think I don't have to say this. It's clear that we need to design methods. There is a need for that. We need to design methods to certify quantum properties in many-body system. And my main message is that I believe relaxations to the problem in the sense that you optimize over a larger set than the actual set is good because it gives you lower bounds to the actual solution. So I think it's much easier to get upper bounds through ansatz. It's much harder to get lower bounds. And this is a promising approach, in my opinion. So using that, I told you how you can apply to the problem of entanglement Bell inequality detection. And we saw that it works well for some paradigmatic examples. And also, we used that in comparison with a quantum annealer, and we could, say, beat it in many situations. But more in general, okay, I think this is a very relevant open problem, how to certify quantum properties of complex quantum systems with our limited classical processing capabilities. That's all. Thank you very much for your attention.